Today we're looking at notes MM-1, RADY, a graphic organizer. So first thing I want you to notice is that T is squared. It really has two purposes. So the T is squared because there are two T's in RADY. One of them stands for tangency and one of them stands for togetherness. And what's really cool is the squared, or an even exponent, is what you're looking for whenever you're looking for those two items in a rational graph. So tangency and togetherness. And we'll talk about that in a minute. So you will look for a factor squared like x minus 1 squared, or basically a factor to an even power will create these things. Okay, so tangency, you're like, well, what the heck is tangency? Tangency is when you bounce off a root, okay? You remember talking about tangent lines to a circle and that sort of thing. So that is tangency, excuse me. Togetherness is when you approach the VA from both sides, or vertical asymptote. So a graph like this is togetherness, where you notice we have this vertical asymptote, this horizontal asymptote, and the graph approaches the asymptote from both sides here, okay? Unlike it doesn't separate, it comes together. Okay, so RADY is a graphic organizer to help you with pretty much all that we've learned with rational graphs. I think you're really going to love this lesson. It's probably my fave. Okay, so the R stands for roots. Remember, you set your numerator equal to 0. A stands for asymptotes, but only vertical. Okay, and that's when you set your denominator equal to 0. T, tangency, you're looking for factors in the numerator squared or even. Okay, togetherness, denominator squared. Okay, factors of the denominator squared. In behavior asymptotes, remember you're going to look at your degrees for those horizontal or oblique asymptotes. Y-intercept is when you set x equal to 0, And then, of course, not in the RADY, you'll want to test to see if the graph crosses the end behavior asymptote. So remember, you set that end behavior asymptote equal to f of x. Okay, so I've written this here to help you a little. Notice, you probably already know what it stands for, but the roots come from the numerator. The asymptotes come from the denominator, vertical. The tangency comes from the numerator, and the togetherness comes from the denominator. And remember, if you're wondering, well, how the heck am I going to remember if tangency or togetherness comes first? Well, alphabetically, tangency would come before togetherness. So that's kind of a cute little thing. And of course, the E and the Y aren't solely dependent on either just the numerator or just the denominator. They're dependent upon both. So let's get to practicing. Sketch a graph for each and identify the RADY characteristics. So remember, we want to see this rational equation written both in factored form, but also where the numerator and denominator are both in standard form. So we are going to multiply, FOIL, 3x minus 3, the quantity 3x minus 3 times the quantity x plus 4. And when we do, we'll get 3x squared. The outer would be 12x, the inner would be negative 3x, and 12x minus 3x would be 9x. And then negative 3 times 4 would be negative 12. Over, if you FOIL the quantity x minus 2 times the quantity x minus 2, you'd get x squared plus 4x and then plus 4. Remember, you need to see this both ways, right? Both ways, always, if you can. Of course, we've looked before where you can't factor. Okay, so write both ways. We definitely want to see both of these. So for roots, of course, we want to look at the factored version. So for roots, we set that numerator equal to 0. So 3x minus 3 set equal to 0 would produce a root at 1. So 1, 0, x minus 4 would produce a root at negative 4. So there's my roots, 1 and negative 4. I think I'm going to go ahead and, well, should I graph as I go? I think it might be hard for you to see, but I'll try my best to fit it all in the screen. So 1, 0, and negative 1, 2, 3, 4, 0. Okay, A, asymptotes, vertical only. denominator equal to 0. So vertical asymptote would be x equals -2. Remember, we have the same, oh my gosh, what am I looking for? The same factor twice, so you don't need to write a vertical asymptote twice. It only happens at x equals -2. There's our vertical asymptote. Okay, remember, tangency comes before togetherness. So it was numerator, denominator, numerator. So do I have any factors squared in the numerator? No, so tangency would be none. Okay, so nothing to worry about there. Togetherness. Do I have factors in the denominator? Remember, numerator, denominator, numerator, denominator. So any factors in the denominator squared? Yes, we have x plus 2, the quantity x plus 2 squared. So you will have togetherness at x equals -2. So at that asymptote at x equals -2, your graph will approach that VA from both sides. And we'll start drawing the graph in a minute, not just yet. So EBA, end behavior asymptotes. Okay, look at the degrees. So to look at the degrees, I find it much easier to look at the standard form in the numerator and the denominator. So definitely my degrees match. Okay, so when the degrees match, it's the EATS DC, it's the divide coefficient. So 3/1. So I'm going to have an HA at y equals 3. Y equals 3 is my horizontal asymptote. 1, 2, 3. So here we go. Alrighty, and then y-intercept. So if I have one, to me, again, it is easier to look at this version. You still could do it from this version pretty easily, but here it's so nice to see if I plug in 0 for x here, plug in 0 for x here, plug in 0 here, plug in 0 here. Of course, all of those terms are gone because they're 0, and you'd have -12/4, which would be -3. So you have that y-intercept at 0, -3. Let me close that parentheses. 0, 1, 2, 3. Okay, so we're getting a good picture of what's going to happen here. So do we cross the EBA? So remember, the horizontal asymptote is 3 equals, again, in my opinion, much easier to use this version. Otherwise, you're going to have to multiply a lot. And we already did it, so why reinvent the wheel? Kind of low on space here, aren't we? Okay, so then over 1. So then 3 distributes to all 3 terms here. So I'm going to come off to the side. 3x squared plus 12x plus 12 equals 3x squared plus 9x minus 12. Oh, goodness. Okay, so then, of course, this and this cross through. And then that's it for crossing through. So I'm going to move this 9x over and make this 3x, because when I subtract, and then I'm going to move this 12 over. I'm subtracting. -12 minus 12 is -24, y'all. We're about to be in calculus. Time to start skipping steps. X equals -8. Okay, so -8 is my point of crossing. Remember, I use the y value. I technically plug this into the EBA, but y'all, there's no x to plug in, so my y value is just automatically going to be 3. So yes, I cross the EBA at -8, comma 3, negative 1, 2, 3, 4, 5, 6, 7, 8. So I cross through right here, and this is making a lot of sense because remember, we talked about we do have togetherness, and we never could graph that because we didn't have our curves yet. So we know now, as we can see, this graph is definitely going to hug like this, because we've got to hug these asymptotes, and then here. Oh, I didn't do a good job of curving it, but we know that it curves around like this, and of course it's going to stick to this asymptote here. Remember, these asymptotes are like magnets, these horizontal asymptotes. So that's about what our graph looks like. So let's do one more example, number 2. Again, write the rational function both ways, both where it's like this in standard form in numerator and denominator and factored. So we definitely want to try to factor what values multiply to 4 but add to 4. So of course that's going to be 2 and 2. So we're going to have x plus 2 squared on top, and then in the bottom you've got values that multiply to -2 but add to -1. So that's going to give you x minus 2 and x plus 1. So for our roots, running out of room. Remember, that comes from the numerator, so our root is going to be -2, 0. All right, and that's that, -2, 0. Asymptote, more specifically VA, look at the denominator. So that's going to give us x equals 2 and x equals -1. X equals 2, x equals -1. Okay, tangency. Remember, that comes before togetherness. And we have tangency at a point. Remember, that's going to be a point. We have tangency at our numerator, denominator, numerator, at -2, 0, because that tangency is like a bounce. So we know this will be some kind of bounce, whether it bounces like this or bounces like that, we'll see. Okay, togetherness, there's none, because we don't have any factors squared in the denominator. EBA and behavior asymptote. So let's look here. We would have an HA at 1 because it's that eats DC situation where our degrees in the numerator and denominator match. So y equals 1. Okay. And then y-intercept. Before I write it, let's make sure we have one. Plug in 0 for x. So 0 here, 0 here, 0 here, 0 here. 4 over -2 would be -2. So we do have a y-intercept at 0, -2. So I'm going to plot that 0, -2. Oops, that's -1. I was counting off the asymptote instead of the x-axis. And then do I cross EBA? Well, let's take that HA1, set it equal to the original given rational equation. Hope, cross our fingers that we have enough room to work here. So it's nice because 1 times all 3 terms, 1 times all 3 terms just basically means x squared plus 4x plus 4 equals x squared minus x minus 2. So our x squareds simplify out. I'm going to move this x over here, so it's going to become 5x equals, I'm going to move this 4 over here, -6. So x equals -6/5. Well, that's just lovely. -6/5 is my x value. If I plug that into my EBA, which there's no x to plug in, I just know my y value is going to be 1. So -6/5 is a little bit more than -1. So I'm going to go a little bit past -1, and then right there is where I'm going to cross. So I don't have togetherness. I do have tangency at -2, so I know that this is going to be like this, and it's going to bounce, And since it can't cross here, remember, it doesn't cross our asymptote anywhere else, so it's just going to ride that line like that. It bounces and then rides. And then here, we don't have any roots here, so we're going to hug here. We can't, maybe we can go up, but we can't go up too high because we don't have any roots. Then we're going to hug there. And then here, we can't have a curve on this part because we don't have any other roots, so we must have a curve here.